Hello students, today we shall see what is curvature and radius of curvature of a plane curve, what is the formula for calculation of radius of curvature and some examples. So first we see what is curvature and radius of curvature of a plane curve. Let capital A be a fixed point on a plane curve and P and Q are two neighboring points on the curve such that arc AP equal to S and arc AQ equal to S plus delta S, so that arc PQ equal to delta S. See in the figure, arc AP is S, arc AQ is S plus delta S, so that obviously arc PQ is delta S. A is a fixed point on the curve. We are measuring the arc length from the fixed point A. Now let psi and psi plus delta psi are angles made by the tangents to the curve at P and Q with some fixed line OX in the plane of the curve. Psi is the angle made by tangent to the curve at P with OX. Psi plus delta psi is the angle made by the tangent to the curve at P with OX. OX is a fixed line in the plane of the curve. Then, what is delta psi? This delta psi is the angle through which the tangent to the curve turns or rotates as the point of contact moves from P to Q through an arcual distance. This arc length PQ is delta S. Through an arcual distance delta S. If the point of contact moves from P to Q through an arc distance delta S, then the tangent rotates through an angle delta psi. According to our intuitive feeling, delta psi will be large or small as compared to delta S, depending on the degree of sharpness of the bending of the curve. See, if the curve is more bent, then delta psi will be large. If the curve is less bent, then delta psi will be small. And this intuitive feeling suggests the following definition. The total bending or total curvature of the arc PQ is defined to be the angle delta psi. This angle delta psi is called total bending or total curvature of the arc PQ. And the ratio delta psi by delta S is defined to be the average curvature. Average curvature of the arc PQ is defined to be the ratio delta psi by delta S. That is curvature per unit length, delta psi by delta S, average curvature. Now if we take limit here, delta psi by delta S, then it will become curvature at the point P. So that is the definition given here. The curvature of the curve at the point P is defined to be the limit delta psi by delta S as Q tends to P. Q is very near to P. Q approaches P. And when Q approaches P, automatically delta S will be tending to 0. Delta S, arc length delta S tending to 0. So this limit is limit delta psi by delta S as delta S tends to 0. But this is the definition of derivative of psi with respect to S. It is d psi by ds. So curvature at the point P is d psi by ds. And radius of curvature of a curve at a point P on it is defined to be the reciprocal of the curvature d psi by ds. Reciprocal of the curvature is called radius of curvature, provided it is not 0. Curvature should not be 0. Only then you can take reciprocal. And it is denoted by rho. Symbol is rho. Thus, rho equal to 1 by d psi by ds equal to ds by d psi. This is derivative of s with respect to psi, ds by d psi. And it is always measured positive. Rho is always measured positive, although curvature may be positive or negative. The word is radius, radius of curvature. So this is how curvature, radius of curvature are defined, but in short, the definition can be given like that. Definition of curvature and radius of curvature. Let A be a fixed point on a plane curve and P be any point on the curve such that arc AP is S, and the tangent to the curve at P makes an angle psi with some fixed line OX in the plane of the curve. Then the curvature of the curve at P is defined to be d psi by ds. Curvature is d psi by ds, derivative of psi with respect to S, and the radius of curvature at the point P is denoted and defined as rho equal to ds by d psi. ds by d psi, derivative of S with respect to psi, but it is what? It is the reciprocal of the curvature, provided the curvature is not 0. So this is the definition of curvature and radius of curvature. Now in this definition, what we have used? ds by d psi by ds. So ds by d psi is derivative of arc length s with respect to psi, with respect to the angle made by tangent with some fixed line x. So what is the meaning? How to calculate ds by d psi? Let us see. Derivative of an arc. Let capital A is a fixed point on a curve in xy plane and pxy be any point coordinate of p x and y, or x and y, be any point on the curve such that arc AP equal to s, and the tangent to the curve at P makes an angle psi with positive direction of x-axis. Okay, then ds by dx is given by this root over 1 plus dy by dx square. ds by dx, derivative of arc length s with respect to abscissa x, is equal to root over 1 plus dy by dx square. What is dy by dx? We know, tan psi, slope of the tangent. But this result also has proof. We are not proving. ds by dx is root over 1 plus dy by dx square. And dy by dx is tan psi, so it is root over 1 plus tan square psi means sec psi. Thus ds by dx is sec psi, so that dx by ds becomes cos psi. Similarly, ds by dy is cosec psi, so that dy by ds is sin psi. So this results to be remembered, and this can be remembered from this elementary triangle. It is not triangle, but when P and Q are very near, then this arc PQ will be almost straight. That's why this looks like a right angle triangle, and the angle made by tangent will be same as this angle psi. This PQ makes an angle psi with PR. Coordinates of PXY, coordinates of Q, x plus delta x, y plus delta y. So PR is delta x, QR is delta y. So the ratio is delta y by delta x is tan psi, delta x by delta s is cos psi, delta y by delta s is sin psi. But if we take limit as q tends to p, or limit as delta s tends to 0, delta x tends to 0, delta y tends to 0, all will be tending to 0 if q tends to p. In that case, this dx by ds becomes cos psi, dy by ds becomes sin psi, dy by dx becomes tan psi. Obviously, we can remember the result from this elementary triangle. Okay, and the relation between s and psi of a curve is called its intrinsic equation. The relation between x and y, x comma y coordinates of any point on a curve, then the relation between x and y is called Cartesian equation of the curve, that we know earlier. And now what we have seen, if the point P changes its position, then arc length s will be changing, and automatically angle psi will be changing. So surely there is a relation between s and psi, and this relation is called intrinsic equation of the curve. And the radius of curvature is defined in terms of intrinsic coordinates actually. So first example, let us see today. Find the radius of curvature at any point s comma psi. This s comma psi intrinsic coordinates, arc length and angle made by tangent. So radius of curvature at any point s psi of the curve s equal to s x psi tan psi plus a log x psi plus tan psi. Number 2, s equal to c tan psi. Number 3, s equal to a e to the power x by c, where x, y and s psi are Cartesian and intrinsic coordinates of the same point. So we have to find radius of curvature of the first curve. It is given in terms of s and psi. So just ds by d psi will give us the radius of curvature. So derivative of s with respect to psi here is sec psi tan psi. Even to b rule, product rule, sec psi remains, tan psi derivative is sec square psi, plus tan psi remains, derivative of sec psi is sec psi tan psi, plus a log sec psi plus tan psi. Log of anything is 1 by that thing derivative into derivative of that thing, means derivative of sec psi is sec psi tan psi, derivative of tan psi is sec square psi. Now this is sec cube psi, tan psi, tan square psi, but and sec psi remains, and then here sec psi we have taken common, so it will be tan psi plus sec psi. You have written here sec psi plus tan psi, all the same, and derivative is sec psi plus tan psi. So these two gets cancelled. And here tan square psi you have written as sec square psi minus 1. So finally sec cube psi means twice sec cube psi, a is there, and minus sec psi, and this sec psi gets cancelled. Here is a, so ds by d psi here twice a sec cube psi, which is required radius of curvature at the point s comma psi. So just derivative of s with respect to psi is the radius of curvature. Number 2, s equal to c tan psi. So directly ds by d psi is tan psi derivative is sec square psi, so which is radius of curvature at the point s psi. Number 3 is s equal to a e to the power x by c. See, this is there is a mixture s and x, s and x. So that's why we differentiate first with respect to x. ds by dx is derivative of e to the power x by c, c to the power x by c into 1 by c. By chain rule, derivative of x by c with respect to x is 1 by c, so it is 1 by c there. Now a to the power x by c is s, so it is s into 1 by c, and ds by dx, just we have seen sec psi, derivative of arc with respect to x, sec psi, and just cross s equal to c sec psi. So this is intrinsic equation of the curve. Now we differentiate with respect to psi. Ds by d psi is c sec psi tan psi, and this is the required radius of curvature. So next example, example number 2. Show that a circle is a curve of uniform curvature. We know bending of circle at every point is same, uniformly bended. Okay. So question is like that. Show that a circle is a curve of uniform curvature and its radius of curvature at any point is constant and is equal to the radius of the circle. That's why word is used, radius. Curvature, radius of curvature of a circle at any point is same as the radius of the circle. That we have to prove. And bending or curvature at every point of a circle is constant. So let capital A be a fixed point on a circle whose radius is A and center is at O. We have taken a circle, radius is A, center is at O. Let AX be the tangent to the circle at A. A is a fixed point on the circle and AX is the tangent. So this AX will be a fixed line. We need a fixed line for giving definition or calculating radius of curvature. Okay. So A is a fixed point on the circle. AX is the tangent to the circle. So this AX is a fixed line. Let P be any point on the circle such that arc AP equal to S. Arc AP equal to S. And let tangent to the circle at P, that is PT here, we have written, makes an angle psi with this AX. Our fixed line is here AX. In the definition we have written it as OX, here it is AX. Now, if this angle is psi, tangent PT makes an angle psi with AX, another tangent AX at A. So then the angle AOP equal to psi. It is easy to see. How? Angle between two lines equal to angle between their perpendiculars. Here, see, OA is perpendicular to AX because OA is radius, AX is tangent, and OP is perpendicular to PT because PT is tangent, OP is radius. So angle between this AX and PT will be same as angle between OA and OP. Angle between two lines equal to angle between their perpendiculars. Okay. So angle AOP is psi, means angle at the center is psi and radius of the circle is A. That's why S, arc length AP, arc length AP, here is S. S is equal to A psi. We know for a circle, arc length is equal to R theta, radius into angle at the center in radian measure. Here angle is psi, radius R is here A, so arc length S is equal to A psi. So this is our intrinsic equation of the circle in this case. S equal to A psi. Therefore, ds by d psi is what? A. Derivative of s with respect to psi is 1. Derivative of s with respect to psi is A into derivative of psi, means psi derivative with respect to psi is 1. So that is answer is only A. So ds by d psi is A. But what is this A? This is a constant. And it is the radius of the circle. Therefore, radius of curvature, because ds by d psi is the radius of curvature by definition. So radius of curvature at any point on the circle is constant and it is equal to the radius of the circle. So second part of the question is proved first. Now we need curvature. Also d psi by ds is 1 by A. This is curvature which is constant. 1 by A is also constant. That is curvature of the circle at any point. D psi by ds is curvature. So curvature of the circle at any point is constant and it is the reciprocal of the radius of circle. Therefore a circle is a curve of uniform curvature. So proved the result. Next, most of the equations of curves are given in terms of Cartesian coordinates instead of intrinsic coordinates. That's why let us find the formula for calculation of radius of curvature in terms of x and y, that is in terms of Cartesian coordinates. So formula for radius of curvature at any point x comma y of a Cartesian curve y equal to fx. Let capital A be a fixed point on the curve y equal to fx and p be any point on it such that arc AP equal to s, and coordinates of p, x and y. And let the tangent to the curve at p makes an angle psi with positive direction of x-axis. Then we know dx by ds is equal to cos psi. Standard result already shown. dy by ds is sine psi and dy by dx is tan psi. Okay, slope of the tangent. Now we need ds by d psi, that is radius of curvature. So this dy by dx equal to tan psi line we differentiate with respect to s. dds of dy by dx is equal to dds of tan psi. Now dds of dy by dx can be written as ddx of dy by dx into dx by ds by chain rule. This is by chain rule. Okay, and right side is dds of tan psi. We can write it dd psi of tan psi into d psi by ds by chain rule again. Okay, details shown here. So ddx of dy by dx means d square by dx square, and dx by ds we know it is cos psi. And here dd psi of tan psi means derivative of tan psi with respect to psi is sec square psi, and d psi by ds is curvature, so it is 1 by rho. Where rho is ds by d psi is the radius of curvature we know, so d psi by ds is 1 by rho. Now from this cos psi when comes here it will be 1 by cos psi means sec psi means sec cube psi, and rho goes there, so rho is equal to sec cube psi by d square by dx square. Now sec psi is root over 1 plus tan square psi and to the power 3 is there cube. Now tan psi is we know dy by dx, so it is root over 1 plus dy by dx square to the power 3 by 2 because root is there 3 by 2 divided by d square by dx square, and this can be written as in short rho equal to 1 plus y1 square to the power 3 by 2 by y2. y1 means dy by dx, y2 means d square y by dx square. So this is the formula for calculating radius of curvature in Cartesian coordinates. We shall have to remember this formula. Okay, now the definition of curvature shows that it is independent of the choice of axis. Why? In the definition of curvature, what we have seen, psi is the angle made by the tangent to the curve at a point P with some fixed line yx. The fixed line may be OY also, maybe y axis also. That means role of x axis, y axis can be interchanged. Role of x and y can be interchanged. That's why the radius of curvature formula, another one we can write rho equal to 1 plus dx by dy square whole thing to the power 3 by 2 divided by d square x by dy square. It was with dy by dx rho, here we can write it with dx by dy. Everywhere x and y interchanged. So this is also formula for radius of curvature, and it is suitable when dx by dy is 0. That is when dy by dx becomes infinite. In some problems you can see that dy by dx becomes infinite at the point where we need the radius of curvature, or in the neighborhood of the point where we need the radius of curvature. So when dy by dx becomes infinite, then we shall take dx by dy, and that dx by dy will become 0 and easy to calculate. So this is formula is also important. Next, two formulae we shall write only without proof. We shall use formula for radius of curvature in parametric form. The radius of curvature at any point on the curve x equal to phi t, y equal to psi t, where t is a parameter. This is called parametric equation of a curve. T is parameter. And in this case, the radius of curvature is given by rho equal to x dash square plus y dash square whole thing to the power 3 by 2 divided by x dash y double dash minus x double dash y dash. Where x dash means dx by dt, y dash means dy by dt, x double dash means d square x by dt square, y double dash means d square y by dt square. X double dash is d square x by dt square, y double dash is d square y by dt square. Second derivative. Dash means derivative. So this is radius formula for radius of curvature in case of parametric curve, that is parametric coordinates, if it is given in parametric coordinate. Next, formula for radius of curvature in polar coordinates. Polar coordinates r and theta. The radius of curvature at any point of a polar curve r equal to f theta. Instead of y equal to fx, the curve here it is r equal to f of theta. This is called polar equation of a curve or polar curve. And in this case, the radius of curvature formula is rho equal to r square plus r1 square whole thing to the power 3 by 2 divided by r square plus twice r1 square minus r2, where r1 means dr by d theta first derivative, r2 means d square r by d theta square second derivative of r with respect to theta. So these two formulae we shall also remember. Now let us see some examples. Example number 3. Find the radius of curvature at the origin of the curve y minus x equal to x square plus twice x square plus y square. For this curve, we have to find radius of curvature at the origin. Means we need dy by dx and d square y by dx square at origin. So that's why we differentiate this line. Here, incidentally, this is x plus y whole thing square. X square plus twice x square plus y square. So it will be easier to differentiate. So differentiating with respect to x, we get dy by dx minus 1. Right side is x plus y square means 2 into x plus y into ddx of x plus y means 1 plus dy by dx. Okay. Without simplification, let us again differentiate with respect to x. So left side will be d square y by dx square. Derivative of 1 is 0, and then here it is u into b. 2 into derivative of x plus y is 1 plus dy by dx. Already there is a 1 plus dy by dx plus twice x plus y remains 1 plus dy by dx. Derivative will be d square y by dx square. 1 derivative of 1 is 0. So this is line number 3 we have marked. Now at origin, that is when x0 and y0. we get from number 2 and 3. In number 2, if we put x0 and y0, right side is 0. So dy by dx minus 1 is 0. So dy by dx is 1. And in number 3, if we put x0, y0, what we get? And this term will be 0. But here dy dx is 1 already we have got. So it is 2 into 1 plus 1 into 1 plus 1 means 8. d square by dx square is 8. Therefore, required radius of curvature is rho equal to 1 plus dy by dx square to the power 3 by 2 divided by d square by dx square. This is the formula for a calculation of radius of curvature. Just putting the value of dy by dx and d square by dx square, we get rho is root 8 by 8 means 1 by root 8, that is 1 by 2 root. Example number 4. Find the radius of curvature of the curve y square equal to 4a square bracket twice a minus x by x at the point where it cuts the x-axis, and it is given that a positive. The curve cuts x-axis at a point, and at that point we need radius of curvature. So curve is given, and this curve cuts x-axis when y equal to 0. At any point on x-axis we know y0. So if we put y0 here, what we get? Twice a minus x0. Therefore x is twice a. Therefore the curve cuts x-axis at the point twice a comma 0. So we need radius of curvature at twice a comma 0. So now we find dy by dx and d square by dx square, first derivative and second derivative. So for that, what we have done, instead of u by v, we can applying v by v, we have simplified it. 4a square 2a means 8a cube by x, and then minus x cancels, it is 4a square. So it will be easier to differentiate this line. So differentiating with respect to x, we get y square derivative is 2 into y into dy by dx, and 1 by x derivative is minus 1 by x square, 8a cube is constant, then 4a square is constant 0, derivative is 0. Again let us, so from this we find dy by dx is minus 8a cube by x square y. 2 and 8 cancel, so it is 4a cube. Okay, 4a cube by x square y. Now in this dy by dx expression, if we put y0, there is a problem. So which is undefined at twice a comma 0, because our point is twice a comma 0. At this point we need radius of curvature. So if I put y0, this is meaningless, undefined. So in this case, or if we take limiting value will be infinite. So in this case, what we do, we take dx by dy. Dx by dy, just reciprocal. So it is minus x square y by 4a cube. Now no problem. When y is 0, the dx by dy is 0. Therefore, we differentiate this line with respect to y now. So dx by dy will become d square x by dy square, and right side is 1 minus 1 by 4a cube constant, x square y, derivative of x square into y, x square derivative is 2x into dx by dy, because we are differentiating with respect to y, plus x square remains, derivative of y with respect to y is 1, so we have written only x square here. Now at the point twice a comma 0, that is when x is twice a, y is 0, so we get here dx by dy is already 0, because y is 0, and d square y by d square x by dy square will be what? Y is 0, so this part will give us 0, and x square means twice a square is 4a square. So 4a square and minus 1 by 4a cube, simplifying we get minus 1 by a. So first derivative, second derivative obtained. Therefore required radius of curvature is, this time we shall use the second formula, rho equal to 1 plus dx by dy square to the power 3 by 2 by d square x by dy square. Okay, dx by dy is 0, d square x by dy square is minus 1 by a, so it is finally minus a. But by convention, rho, radius of curvature, is measured positive, so we shall write rho equal to a only. Okay. Example number 5. Find the radius of curvature of the following curves at the indicated point. 9x square plus 4y square equal to 36x at the point 2, 3. So this will be similar to example number 3. Just differentiate this equation with respect to x 2 times, you will get dy dx, d square y dx square, and then you put x 2 y 3, you will get value of dy dx, d square y dx, etc., and put in the formula for radius of curvature. Directly you will get rho equal to 4 by 3. Okay, similar to example number 3. Example number 3, we have done radius of curvature at origin, means differentiated and then finally taken x0 y0. No problem faced there. Here also for this example number 5, Roman 1, you will see similar thing. Roman 2 is y square equal to s square into a minus x at the point a comma 0. We have to find radius of curvature. So this will be similar to example number 4, means this time you will see that dy by dx will become undefined at the point a comma 0. So that's why we shall take dx by dy, and dx by dy will be 0, and then you will calculate d square x by dy square, you will get minus 2 by s square, and then putting this value in the second formula, means similar to example number 4, the rho will be s square by 2, because by convention rho will be taken positive, that's why that minus sign will not be in the final answer. Okay, so thank you for today. Some more examples we shall do in the next class.